Welcome to ACS Webinars, bringing you the best and brightest minds in chemistry, live every Thursday at 2 p.m. Eastern. To view our upcoming schedule, please visit acs.org/acswebinars.
I'd like to introduce Andrew Bocarsly to you very quickly. Andrew earned a bachelor's degree in both chemistry and physics from UCLA just a few years ago. He carried out his PhD research in physical chemistry at MIT, and since the early 1980s he's been a member of the faculty in Princeton's Department of Chemistry. Prof. Bocarsly has published roughly 200 research papers in peer-reviewed journals. He's an inventor on 6 issued patents. His research focuses significantly in materials chemistry associated with creating membranes for use in developing new fuel cells. And applications of his work include converting carbon dioxide to various alternate energy companies. He's a founder and president of the Science Advisory Board for LIQUIDLIGHT Incorporated, and it's a company formed to commercialize the production of organic commodity chemicals from carbon dioxide. In terms of awards, Professor Bocarsly has received an Alfred P. Sloan Fellowship. He's also received the Sigma Xi Science Educator Award for the Princeton section and the ACS Exxon Solid State Chemistry Award, and he is an editor for Methods in Materials Research. We're going to have a great time. The attendance is fantastic, and there's an awful lot of people interested, and we've had a wonderful time just listening to Prof. Bocarsly getting ready for this. So the floor is now yours, Andrew.
Thank you very much, Joe. And first, I'd like to thank you for giving me the opportunity to speak with our audience today. I've been looking forward to this. As you mentioned, I'm wearing 2 hats today as I speak to you. One is as a professor at Princeton University, and the other as being involved in the founding of a startup company, LIQUIDLIGHT, which is trying to commercialize the chemistry we've been working on at Princeton. I'd like to share both aspects of what I'm doing with you this afternoon. This issue, which we were hearing about just a couple moments ago, about CO2 in the atmosphere, really is a chemistry issue. I'm showing you here an article published by someone I think we're all familiar with, Arrhenius, back in 1896, one of the few publications he wrote in English, actually. And he did that because he was collaborating with some Americans, and he was in Philadelphia when he wrote this article. So he had discovered that he could calculate how much CO2 was in the atmosphere because Beer's law had been discovered. And he realized if he looked at the moonlight as a source for use and used Beer's law, if he used 2 different positions at intensity of moonlight, he'd figure out how much CO2 was absorbed. So he came here to get that data because it was available through the Naval Observatory, and he published this paper about how much CO2 was present, and we already heard those numbers in the couple hundred parts per million level. And then at the end of this paper, and you'll notice this article really is an 1896 article. It doesn't say CO2, it says carbonic acid in the air, but that's what we call CO2 today. At the end of the article, he says, you know, this is going to keep going up because we're burning a lot of coal these days because we use a lot of energy. And as we burn that coal and more CO2 is generated, the atmosphere is going to get warmer and the ground temperature is going to rise. 1896, this was predicted. And the only issue he deviated from the more recent story is he said, this is probably good news in this article, he states at the end, because as the climate becomes more temperate, we'll be able to grow more crops, and that will be good because we have an increasing population, we'll be able to feed everybody. So we now understand that, in fact, there's a downside to things heating up, but it's been an issue that's been around for a long, long time, and it's thanks to a chemist, actually, that we know about it. Okay, so what are we doing? Let me start off telling you a little bit about this. Our theory is that we have this CO2, and you can look at it as a pollutant, or you can look at it as an opportunity to do something new and interesting. That is, it's a chemical, it's a reactant. Let's make something with it. So at Princeton, we have this requirement for our juniors, and they have to do a so-called junior paper, which involves meeting with a professor in a tutorial style and talking over some interesting chemistry, going to the library, doing some research, and coming up with some conclusions that one writes a paper about. So a few years back, I had 3 students. I'm calling them students A, B, and C. And I said, oh, I have 3 of you, so let me give you an assignment. I'm going to have you all go to the library, find some interesting CO2 chemistry, come back, we'll discuss that chemistry amongst ourselves, and then we're going to take a little vote and see which chemistry would be the right chemistry to pursue in terms of getting rid of the CO2 that we have in our atmosphere that we're not so happy about. So one student came back and she found some really interesting chemistry that's been going on up at Cornell by Professor Jeffrey Coates. And he's been reacting carbon dioxide with various natural products. And in this particular case, it was a molecule found in the skin of limonene. And he was able to make a polymer which had wonderful plastic properties. So she said, we can make this polymer, and then we can take it, since it's moldable, and we'll make Tupperware with this material. Now, I had a second student who went and he read some articles indicating that CO2 could be reduced down to carbon black. And he pointed out carbon black is the coloring agent in tires that makes them black. And he goes, we need a lot of tires, so that'd be a great place to stick our CO2. Let's stick it in tires. And then finally I had a third student, kind of, yeah, and you know this kind of student. He said, Professor Bocarsly, obviously we should do your chemistry. Got a lot of brownie points there. Actually, he liked it so much he ended up working in my lab. But he suggested we turn the CO2 into methanol, which is one of our big products. And since methanol can be used as a fuel, we have a new fuel source. So at this point, I'd like to hear what you think the correct approach is. And so I'm going to turn things over to Joe.
Thank you, Andrew. So we have 3 choices here. And audience, let's see what we all think. We can have a choice of reacting CO2 with a natural product found in lemon to make polymers, and essentially we can make some Tupperware. Second is that we can use CO2 to make some carbon black, and our third choice is converted to that commodity chemical that's needed throughout the world, methanol. And while you think about that, please make your selections quickly and answer. We'll see how the poll goes. But I'd like to give a really quick shout out to the chemistry folks at Lakeland College. You've been really good attendees, and we love having you here. But I'm going to count down now and give you 5 seconds to answer, and we'll see how the poll results go. So we'll count down from 5, 4, 3, 2, 1. And now let's close the poll and see how the answers look. And so we've got oh goodness, a lot of people there must be a lot of college students who are looking for good grades today, because we've got a 16% share of the audience that says make some Tupperware. Now, obviously 6% of the audience is thinking that there's not a huge demand out there for carbon black because they were the ones who chose this. And we've got fully 78% of today's audience who said, let's convert it to methanol. So back over to you, Andrew.
Very good. Okay, so before we answer this question, I have to tell you one more piece of information. A 1 gigawatt coal-fired power plant, and we have many of them of that size in this country. It's big, but we have a lot, especially in the Midwest, generates 1,000 pounds of CO2 per second. Okay. That picture I'm showing you, of course, is not the CO2 coming out of the stacks. That is a power plant. That's the water coming out, but there's an equal amount of CO2 that you can't see. Okay. So when I mentioned this to the 3 students, the student who suggested the Tupperware came back with the following statement: no one can use that much Tupperware. In fact, that's exactly the right answer. There isn't an answer to this question per se. There are lots of answers to this question. We generate so much CO2 in such a short period of time, there's not a single individual thing you could think about doing that would use up all that CO2 and not cause some new kind of problem. And so one way of thinking about this is to think about how we currently use petroleum and its products. Right now we're worried about mitigation of CO2. One of the early suggestions, which is still being vigorously pursued, is we should simply take that CO2 and hide it somewhere. That's called sequestration. And the favored place to hide it at the moment is deep underground. And I think that has some problems. One of it's rather expensive approach. Second is you have to guarantee that it stays underground. And it's actually the other approach is what I've been suggesting, which is let's turn it into something else that's useful. If we're going to do that, we might model that after how we use petroleum right now. And it turns out that 7% of the petroleum that we are gaining today is used to make various, I'll call them soft materials, polymers, Tupperware, things like that, caulkings, various materials like that, plastics. And then 93% is used to make fuels. Now the downside, of course, of making a fuel is that you're going to burn a fuel and make more CO2, but the only way you can really use up a significant amount of the CO2 is to make a fuel. So you should do the other things. You should make the Tupperware and the tires and all those other wonderful things that you can make from CO2, absolutely. But in addition to that, you're going to have to make fuel if you want to use up the CO2, and then regenerate that CO2 and use it again, set up a cycle. Okay, so our goal is to think about that fuel side of the reaction for a few minutes. And the simplest thing that one can think about making is methanol, which could be used directly as a fuel, could be used, there's a process available that will turn methanol into gasoline, so you could take it that route. Or, as Joe mentioned a couple minutes ago, methanol might be used on the other side of the equation also and turned into a wide variety of products. It's a versatile reagent. We're going to do this electrochemically. And so we're going to have an electrochemical cell, which you recall has an anode compartment and a cathode compartment. Cathodes where reduction takes place, so we're going to take that CO2 under acidic conditions, combine it with 6 electrons and make the methanol we want. And on the other side, the other electrode is going to be oxidizing water to oxygen. So we'll end up with making methanol and oxygen in a scheme, very much like natural photosynthesis. I could argue, sort of, that since sugars, and I'm pushing it here, I know, but since sugars are defined as a certain carbon to oxygen ratio, that methanol is the simplest sugar. As soon as we start making other alcohols, that's no longer the case. But we're essentially doing a process that mimics artificial photosynthesis in terms of the reactants and the products, but does not mimic artificial photosynthesis in terms of the actual chemistry that is occurring. So let's take a look at that. Now, before you do this in too much detail, one has to consider exactly what the cost is. And to me, there's 2 issues of cost. It's not dollars and cents. One is how much energy does it take? And then the second issue is how much CO2 might you generate inadvertently by generating that energy. So we're going to assume for a moment that the energy source we're going to use is a gas-fired power plant, which is one of the cleaner types of plants we have available in the United States and throughout the world. So we're going to take CO2 as shown on the screen and water. We're going to react it with 6 electrons and 6 protons to make methanol and oxygen. And all I'm showing you there is the thermodynamics of the process. It's uphill energetically. It costs 690 kilojoules per mole to do that. And if we get our electricity for doing that from this gas-fired power plant, that means it generates 2.25 moles of CO2 for every mole of CO2 I get rid of. So this isn't looking so good at the moment, but the story is actually worse than that. Because I need more than just the thermodynamic energy to carry out this process. If I want this reaction to happen at a reasonable rate, I need to supply some more energy to get over the activation barrier for the reaction. Electrochemists call that overpotential. So we have an overpotential we have to deal with, and that's shown here. In terms of the oxygen side of the story, water to oxygen, nobody's ever been able to do that with less than another about 0.4 volts of overpotential. And in terms of the CO2 side, prior to our work, it's been about another volt. So another 1.4 volts is needed here. That's at least, being very, very conservative, 170 kilojoules per mole. I'm probably off by a factor of 3 or 4 there actually in the wrong, and that it's much higher than that. But if I could do it for 170 kilojoules per mole, that would cost me another half a mole plus of CO2. So you can see the arithmetic on the right-hand side of the screen. I'm getting rid of a mole of CO2, but to do that, I generate close to 2 moles of CO2. So this, from a standpoint of getting rid of CO2, does not work too well. So the answer is very simple. I can't use a fossil fuel source to generate the electricity I need to carry out this process, or else I lose. Nonetheless, the energetics I've shown you on the left-hand side of the screen are true no matter what my source is. So let's say I want to do this with light instead. If I want to do it with light, then I need a photon that will take me from the low energy side of the screen to the top up here, the high energy side. That turns out that's a 3 electron volt photon that's in the UV. So this would be a great process to carry out if we lived on the moon. But here on the Earth, our atmosphere more or less screens out those photons, which is really good news in terms of us being able to sustain life here, but is not good news for my process because I can't use the light energy I need to carry out this process. It just requires too much energy to do it. Well, you can see the real problem in all of this is in that yellow box up there. That is, if I could shrink that yellow box, then I could use lower energy photons. I don't have to get rid of the yellow box, it turns out, to do it. I just have to shrink it. And in addition, the good news is that that's the part of the reaction which we as chemists can control. The bottom part is the thermodynamics. We're stuck with that. But that yellow box, we can shrink by finding a good catalyst. And if we were very successful in finding that catalyst, we might shrink it to 1.6 electron volts. Those are red photons. We have lots of those hitting us here, so that would work. But we don't even have to be that good. We could drop that number to about 1.8 to 2 electron volts. Those are the yellow-green photons that our sun likes to give us, and we'd be just fine. So if we can carry off, if we can knock about an electron volt off this process, we could carry it out using light. So we have to find a catalyst that does that. And I'd love to be able to tell you I sat down with my students and thought about this and we came up with the answer, but it is quite fortuitous. There's no thinking involved, just a very clever observation by one of my graduate students back in the early 90s, Lin Chao, who came to the discovery that protonated pyridinium, carried out this reaction. This, by the way, is a very, very unlikely molecule to be a catalyst for this. It's a 1 electron charge transfer reagent. That is, pyridinium can only be reduced by 1 electron. That's all it does. And I've already told you this is a 6 electron process. So this is a real surprise to discover this as a catalyst. But it's a wonderful catalyst for the process. Let me just show you sort of in picture how this all works. And what I've done here is instead of taking just pyridine, we've taken 4' bipyridine, which also works as a catalyst when it's protonated, and has the nice attribute that when I reduce that by 1 electron, it turns blue. And in this case, the molecule could actually be reduced by 2 electrons, in which case it turns yellow. So I start off with a little electrochemical cell, which is shown on the the left-hand side of your screen. It's got 2 electrodes in it. It's got pyridinium, this pyridinium in there. It's got some water in there, and it has no CO2 in there. It has argon in there as inert gas. And it has 2 electrodes in there. And I turn on those electrodes and I reduce the pyridinium that I've generated, and you see that nice blue-violet color that is generated. And I'm making no yellow color. I'm keeping it just that blue color, so the 1 electron reduced product. And at some point when it's a nice blue color, I turn off the electrodes. So there's no more electricity being added to the cell. And now I switch from argon in that cell to CO2. And you'll notice as I do that, the solution starts to fade. And as time goes on, it fades all the way to the final panel. And when I get that final panel where there's obviously no blue color left, I look and see what's in that cell, and I discover that the pyridine is still there, or the pyridinium actually, and in addition to that I have methanol. So you can see mechanistically what's happening here. First I take an electron from my electrode, I drop it onto my pyridinium species, reducing it by 1 electron, and then it transfers its electron to CO2 somehow. I have to do that 6 times to get down to methanol, and then we have methanol. And one might think that's a very inefficient process, but as I already told you, it turns out it's a very efficient process. It turns out the pyridinium is actually acting as 3 catalysts, not 1 catalyst. In the first step, the CO2 is actually reduced to formic acid by this pyridinium, in just exactly the process I told you about. In the second step, the reduced pyridinium, pyridinyl radical, reacts with the formic acid, undertakes a 2 electron charge transfer to make formaldehyde. And then finally, the formaldehyde again reacts very rapidly, actually, with more reduced pyridinyl to generate the methanol. And so not only can we generate methanol by this scheme, but we can make these other products also. In particular, formic acid is a good target. The formaldehyde is a little harder because it's so reactive, but we can certainly go through the generation of formic acid and methanol using this 1 catalyst. Okay, now, I told you I want to do this with light, and I want to do it electrochemically. So the way we're going to do that is in a cell called a photoelectrochemical cell. It's a standard electrochemical cell with 2 electrodes in it, a cathode and an anode. But in this case, our cathode is made out of a semiconductor. And that semiconductor can be irradiated, and right here is the, let's see if I can find my little arrow. Right here is the cathode in this particular experiment. It happens to be made out of P-type gallium phosphide. And it's being illuminated by this source here, which is a blue light source. Little LED, which if you've ever had a filling at the dentist's office in recent years, it's the same thing they use to cure the epoxy. This is called dental blue. Cure the epoxy in your mouth for that filling. We're irradiating that. When we irradiate this semiconductor, it generates electrons. So we don't need an external source of electrons now. And this cell is making CO2 in the presence of pyridinium into methanol. Counter electrode is a carbon electrode, which is hidden in the backside of the cell here. It's hard to see, and we have oxygen evolution from that electrode. This particular cell, which we wrote a paper on in JAX, is a highlight for us because it uses 96% of the electrons generated to convert CO2 to methanol. So basically, all of the electrons we're generating here are converting CO2 to methanol, and it's doing a pretty good job of generating electrons from the light. So we get about a 10% energy conversion efficiency for making methanol in this particular cell, which is an impressive number if you're doing solar conversion. Okay, so that's how this scheme works out. Now, there's another way you could do this. Instead of using that fancy semiconductor electrode, and by the way, I should point out to you the scale on that last slide I showed you, that little piece of semiconductor is a couple square millimeters. It's just a tiny little thing. Okay. Well, we like to scale this up. So another way we might do this is we might take whatever renewable source of energy you want, wind, solar, you could use nuclear, anything as long as it's not a fossil fuel, generate electrons that way separately, feed those electrons into a standard electrochemical cell that has metal electrodes in it, have an anode compartment where we're taking water to oxygen, a cathode compartment where we're taking CO2 to our desired product, find our CO2 from a waste stream such as that coal-fired power plant I was talking about earlier, and generate our fuel. So this is the scheme that is being used at LIQUIDLIGHT. Does not involve a semiconductor, or does actually because we're using a PV panel, but not within the electrochemical cell. We're optimizing the electrochemical cell at LIQUIDLIGHT. And here's one of our first high-throughput cells. It looks a little bit different than the system I showed you in that little round-bottom flask a moment ago. There's the cell actually right there. The rest of the equipment is control equipment. This is a flow cell where an electrolyte is pumped, there's the pump, through the cathode compartment. The electrolyte has been pre-purged with CO2. And this particular cell is set up to make formic acid. And as you can see, this cell we've run for what I would call reasonable periods of time, that is days, sort of 10-day type periods, not the months or years that a real system has to be run at, but it's shown a good degree of stability. And we're getting current densities, you'll notice down here, of 100 milliamps per square centimeter, which is our target current density for such cells. Here we're just using electricity out of the wall, so just to test out the cell. But this is a demonstration that, in fact, you can make a cell. 100 square centimeters is sort of the smallest production size cell one can use, and that's what we have in here, 100 square centimeters of electrode area. And it works. We can efficiently make formic acid in this case doing this. Now you can take those cells, those 100 square centimeter cells, and you can do some plumbing and some electrical work, and you can stick them together. And so here are 3 cells, and they are therefore a stack of cells. And we've stripped out, in this particular case, a lot of that control equipment we were showing you before. We have some plumbing back here just to duct in our CO2 water, basically our seltzer, and our water on our anode compartment. That's going to make oxygen. And our control basically is just these voltmeters that you can see down there. We're not doing anything special. The only additional thing we have here is a little pump to get that stuff into those cells. And we've taken these cells and we have hooked them up to a silicon photovoltaic array that has been very generously supplied to us by PSE&G. If you're from New Jersey, you have seen these panels And I'm showing you going up on the telephone poles all over the state. Whoops. PSEG is using these already to generate electricity. We're taking one of these. There's your 3-cell stack, and we have used this to generate formic acid. And we can do that with an energy conversion efficiency of 1.8% using actual sunlight, just like you're seeing there. The sun is shining on that, and we're making formic acid. And 1.8% may sound like a small number, but this is a very exciting number because about 6 months ago, Panasonic came out with a photoelectrochemical cell based on a gallium nitride semiconductor for taking CO2 to formate. And they touted that cell as the world's best cell for doing this with a 0.2% conversion efficiency, as opposed to our 1.8% approximately conversion efficiency. The Department of Energy has a similar benchmark. They would like to see in their labs out at Berkeley a 1% conversion efficiency for CO2 to methanol. Now, we're not making methanol in the cell, but formic acid isn't far away, as I've already stated. And we've already beat that milestone also. So we're extremely excited about this. This is actually work that was carried out at the labs at LIQUIDLIGHT and involved LIQUIDLIGHT scientists and Princeton scientists, and as I said, a very generous donation of a loaner of one of these wonderful PV cells. Now, by the way, that 1.8%, where's most of that energy going? That PV cell right there, even though it's a great PV cell, is basically wasting about 85% of the light that's hitting it. So that's our big loss in the system, not our electrochemistry. So this is all very doable. Not only can one think about in the future making solar fuels, you can do it today. And LIQUIDLIGHT is doing that. So if we can make solar fuels, like we make C1 products, then there's a variety of things that one might think about making. So let me turn the mic back over to Joe to get some more information from you.
Okay, audience, let's see what we can do about answering this question then. Which one of these C1 compounds has the best production cost to market price ratio when made electrochemically from CO2? So the poll is open, and please select one of these answers that we have here, choosing from carbon monoxide, formic acid, formaldehyde, and methanol. So let's give ourselves a few seconds to think about this. Please choose, and I'm going to be counting down in just a second now before we close the poll from 5, 4, 3, 2, 1, and closing the poll. So there's a lot of, it looks as though we've got a good spread of the selections here. 11% feel as though carbon monoxide conversion is the most efficient. 37% is choosing formic acid with the best production cost to market price ratio. 16% choose formaldehyde, and 36% go with methanol. And so we now turn the mic back over to you, Andrew.
Okay, thank you. So one way of looking at this electrochemically, and this involves a little bit of thinking about the problem, is the most expensive reagent you're using in carrying out this conversion is the electricity. It's the electrons. And so you notice, well, if you make carbon monoxide or formic acid from CO2, those are both 2-electron processes. So it uses 2 electrons worth of electricity. If you make formaldehyde, that's a 4-electron process, and methanol is a 6-electron process, as we discussed. So in terms of the electricity cost, methanol is the most expensive, okay? And that would suggest either carbon monoxide or formic acid might be the best things to make. Now for the rest of the answer, you have to go and look at what the actual market price for these things is. And methanol, by the way, today is made from syngas, which is a mixture of carbon monoxide and hydrogen, and so that's not going to win. It also tells you that carbon monoxide is probably going to be a problem since syngas is readily available from petroleum at a very inexpensive price. And therefore, formic acid uses the fewest number of electrons and gives you the best market price. So formic acid, number 2, is the right answer to that. And that is why LIQUIDLIGHT has set up that demonstration cell that I just shared with you. Okay, let's see. So in carrying out this research, we made a very, very interesting discovery fairly recently. Instead of using that gallium phosphide semiconductor that I showed you a moment ago, we said, one problem with the gallium phosphide is it only responds to blue light, and that's why I was using that denser blue light. We want something that does a better response to sunlight, and so we switched over to P-type gallium arsenide. And we ran our gallium arsenide cell, and I'm showing you some data here. If you look at the black curve here, that's just the cell with no light shining on it. And until you get to very negative potentials here, nothing's happening. So it's a photoelectrode. It's doing nothing in the dark. We're now going to add some of our catalysts to the system and turn on the light. And now we can use just a light that simulates the sunlight. This has got a nice solar response. And we get the the red curve here. And now we're seeing this bump, which is the reduction of that pyridinium, our catalyst, to the pyridinyl. And we can see there's a nice photocurrent here compared to the dark. And finally, we add the CO2 in, and we see the current even gets bigger. And when we go into the analysis of what's in our electrochemical cell after we add the CO2 and the pyridinium, we find that this particular cell is taking CO2 to formic acid. That's fine. It turned out the cell was a little unstable, so we decided to stabilize it by decorating the surface with a little bit of platinum. Not enough platinum to cover the whole surface, but just little particles of platinum, not nano, just little particles, a bad coating of platinum on the surface. And then we ran this experiment again. And when we did this, we got an amazing result. There was still a little bit of formic acid we were forming, but we started seeing butanol as one of the products being formed in this cell. You can see that by NMR is shown on the screen. So suddenly, we also saw isopropanol and acetone in this system. And after running a series of cells, you can see here, these are the numbers we came up with. We still make a little bit of formic acid, 14%. A little bit of acetic acid creeps into this cell. Electrochemically speaking, and I apologize to any organic chemists listening, acetone and isopropanol are basically the same thing, because they're redox partners with each other. So 60% of our electrons are going into acetone and isopropanol, and then you can see on the far right, 20% going into this butanol I mentioned to you. Now the thing that's super exciting about this is we're making carbon-carbon bonds in all of this. Okay, so most of the chemistry on CO2 before has been limited to just doing C1 chemistry, but here we find that this pyridinium catalyzed system generates carbon-carbon bonds. And we found several systems now, not just this exotic gallium arsenide, that in combination with pyridinium and other aromatic amines starts to generate carbon-carbon bonds. And the real big excitement here from a fuel point of view is that if you go and talk to chemical engineers that do combustion research, they will tell you butanol is the smallest molecule they consider a fuel. So we've made a real-life fuel from sunlight here and CO2. And if you go and talk to chemists, of course, you start telling them that you have a new source of acetone and isopropanol as well as butanol, then they can find out all kinds of clever things to make from that. So we've enabled the synthesis size of the chemistry with all these CC products also. So this is an extremely exciting result for us, and we're pursuing this vigorously both in our labs at Princeton and at LIQUIDLIGHT as we do this. And so there, just to highlight the C3 products for you, and the C4 product. Okay. Now, one question when you do all this is, did you accidentally get some of this stuff in your cell somehow? Did someone walk by and spill some butanol into your cell, or maybe there is an impurity because your cell is made out of various sorts of plastics and whatnot, and maybe some butanol leaked in from some leaching process or decomposition of things you make your cell out of. You can imagine many ways this has happened. So we're very confident in the particular result I just shared with you, because what I'm showing you here is a mass spec of our product in which we started with C13 labeled CO2. And that peak I'm showing you, the large peak there, is for C4 all being C13, and the adjacent peak is having 3 of the 4 carbons being C13. So, and we do have a slight amount of CO2 that does leak into the cell, that's C12CO2. So there is absolutely no doubt that this particular cell is taking the CO2 that we put in and is converting it into butanol. Okay, with that, I need to stop talking. Before I do that, I need to thank a whole bunch of people that really did the research. So on the left-hand side of your screen, you see my research group, and in that bottom picture on the right, Emily Cole was the student in my group that did the gallium phosphide work, And Kate Keith on the left did the gallium arsenide work I told you about. And then the remainder of the work was carried out by a large number of the students that are shown up here, but I want to in particular point out this guy right here, Jake, and standing next to him, Jim, who did that work with the PSE&G photovoltaic cell. On the right-hand side of the screen, are the starters, the founding group at Liquid Light. Emily, who started off as a graduate student in my group, has graduated several years ago now, and she is the principal scientist at Liquid Light. And she was joined by Shiva, another PhD scientist from Berkeley Lawrence Livermore Labs, and the president of the company, Kyle Teamy, standing back there. I think this particular was so early in the experience at Liquid Light, about 2.5 years ago, that we filled it with other people. But really, the people doing all the work were those 3 people. I'm happy to report today, the rest of us are just advisors, you can see me there. Today, Liquid Light is a company of 30-plus people with Emily and Kyle at the helm. I also have to thank Liquid Light for providing funding for our labs at Princeton University to carry out this research. And then we have Kyle, the key person, and Emily and Shiva, real background. But of those 32 people that are working there today, most of them are either engineers or chemists. So it's a very serious process now. In addition to Liquid Light, there's a variety of U.S. government agencies that have helped us do this chemistry: the National Science Foundation, the Department of Energy, and the Air Force Office of Scientific Research.
Thank you for watching this presentation. ACS Webinars is provided as a service of the American Chemical Society as your chemistry source for live weekly discussions and presentations that connect you with subject matter experts and global thought leaders concerning today's relevant professional issues in the chemical sciences, management, and business.